Hello everyone, welcome back to the channel. So today we will talk about non-uniform load application. Actually, I am particularly interested in sharing a method that I have came across recently. So this method may reduce the assignment of these non-uniform load application by around 50%. So let me first share with you how I traditionally used to model these non-uniform loads. So here as you can see that I have already modeled a structure with the underground water tank and an overhead water tank. So I'll be applying fluid loads in the overhead water tank using the traditional method. So as you can see, I have the modeled the overhead water tank walls, but along with the overhead water tank walls, I have also modeled some frame elements. These frame elements are only used to carry the non-uniform loads and then transfer it to the walls. So what I have done is I have defined dummy columns. Here you can see that I have named them dummy columns and they have a cross-sectional value of 0.01 inch of depth and 0.01 inch of width. So in this way they have extremely low stiffness, and all they are doing is they are carrying the frame loads and then transferring it to the adjacent walls. Let's go to the load assignment and then frame loads. We'll be reviewing the fluid overhead water tank case. So here you can see that these loads are applied in a varying distributed pattern. So the pressure is at the maximum at the bottom of the tank with a value of 0.49 kip per feet, and it is lowest at the top. Since we know that the fluid pressures are calculated in per feet of the wall, so we have distributed these columns along per unit fit. Let's just analyze this and check the result once. And let's check the deflected shape for the case of fluid overhead water tank. So as you can see, the deflected shape is quite reasonable. So let's check the value at this face of the wall. At this point, so we can see that the value of ux is minus 0.011772. So let's just keep that in mind for some time. And now let me share with you the method that I have came across that I think is quite beneficial. So in this method, we don't have to create any dummy columns, neither we have to distribute along the walls. What we have to do is we have to apply the non-uniform loads directly to these shells. So how we can do this is we can go to the assign menu. So let me first unlock this model. So we have to go to the assign menu, then shell loads, and then non-uniform loads. So in this method, we will use this option. So here we have to select the option of fluid load, the load pattern of fluid over water tank. So in this method, we have to actually solve a system of two linear equation, and then we have to get the value of C and D of two coefficient, and then we have to assign these values here, so the load will automatically be applied to the walls. So I have actually this is very easy, but just for the sake of presentation, I have prepared this mathcat sheet, and I will also attach this mathcat sheet with in the description of the video, so you guys can verify it and use it in your upcoming projects as well. So here the highlighted values that are shown in the yellow, they are actually the inputs. So you can see the density of the water or soil is required, active pressure coefficient Ka. Here it is 1 for the water, but in the case of soil loads or other viscous fluids, this may change. So depth of the water, and that we have to apply. So as we know that the fluid loads vary with the height only. So these x and y values will automatically become 0. So then we will be remaining with the simplified equation of pz is equals to cz plus d. So now, as we know that the pressure at the bottom of the tank will be the maximum and the pressure at the surface of the water will be 0. So we will use these 2 points, these two known points to calculate the value of C and D. So as we can see in ETABs, height is controlled by Z coordinate, therefore the bottom of the tank. Since we are working with the overwater tank, so the Z value for bottom of the tank is 34 feet. Here you can check that the Z coordinate for the bottom of the water tank is 34 feet. So we'll put the bottom of the tank at 34 feet, and then the water pressure. We know that the water pressure we have already calculated for 12 feet of height. The water pressure at the bottom of the tank will be 748.8 psf. So putting these values in this equation, we will get a equation of 748.8, and then at the z variable we'll put the value of z, that is 34, then c plus d at the top of the water tank. So at the top of the water tank, the z coordinate will be the bottom of water tank plus height of the wall, so that will be 46 feet. So the height will be z1 equals to z plus h being the depth of the water or the height of the wall. Here we are not using any freeboard, so we are assuming that the height of the height at which the water can reach will be equal to the height of the wall. So at the top of the water tank, over water tank, and the pressure will be 0. So here the equation will become 0 and the z value will be 46 and c plus d. We will solve these two linear equation to get the value of c and d. So here the value of c and d will be we will have an output of c and d. So the final equation will become pz is equal to c z plus d, and the value of the c and d will be put into the respective variable. So now, once we have these values of the variable of C and D, we'll go back and then put these values here. And there is one thing that is important to know, that the direction, basically it is important then where we are actually applying this load. For example, in this case, let's go to, so in this case, as we know that this yellow axis of local plane of wall shows the third axis of local, that is the local 3 axis. So since our fluid loads are applied outward of the wall, so we have to assign a negative sign to the value of d. So in order to get the negative value of d, that is d should be minus 2870, we have to multiply this whole equation by minus sign. So when we multiply this whole equation by a -1, so we will get the c value as positive 62.4 and d value as negative. So we will apply that here. So once we will apply that, we will get a, since I have already applied the load, so we will get a value of something like this. Fluid overwater tank, you can see non-uniform load direction, local third. So here you have the value of the loads applied, 62.4 as the C value and a D value as minus 2870. As you can see that the other coefficient, X and Y coefficients are 0. You can also check that here as well. So the direction is a local third, the C value is 62.4 and the D value is minus 2870. So now let's analyze this as well, and then we'll compare the values of the deflection in both of these models. So let's check the deflection in the fluid overwater tank case. So let's check the value here. This is the same point where we have calculated the value in the traditional method. So the ux value is minus 0.11758. So it is very close to the value that we have determined there. So they are not very different. I mean, but as you can see that this require quite low effort rather than uh, creating the dummy columns and then assigning them along the wall. We don't have to do that here. And also this method is scalable, and the traditional method is not scalable because if the length of your wall changes, you have to again assign the dummy columns along the length, add those columns, and then apply those loads. But here, if the area of your tank is changing, I mean the length of the walls are changing, then you don't have to do anything. However, if the z coordinate is changing, if the height of the wall is changing, then you have to put the new z values in this equation, and then calculate the equation again. So this is from my side. Maybe if you guys have found it beneficial, just like it and subscribe it. So I'll be trying to come up with similar things, hopefully. Take care. Hopefully we'll see you in the next one. Bye.